Hello, welcome to the Kaggle House Price Challenge using machine learning with Python video. My name is Brandon Hart of the Data Ninja YouTube channel. And if you stumbled upon this video because you did a search on machine learning or Python, just to give you some background, what the Kaggle House Price Challenge is a challenge sponsored by Kaggle. Kaggle's a website that has various data science competitions. A lot of them pay very good money, and some of them are just out there for you to practice and sharpen your skills. So what I intend to do is give you all my code here. It's on GitHub, blhart216 Kaggle House Prices. You can pull that down. And you can watch the video at the same time. And then what I'll do is kind of show you my results, show you my solution, give you some of my thoughts and different decisions that I made at various points. So what we see here is a snippet of the Kaggle website on the house price challenge. And you can see that the ask is very simple. All we have to do is predict sales prices of houses. If we click on a data tab, we'll find out that there's two main files we'll be working with: the train.csv, the training set, and the test.csv, the test set. Now, because this is supervised learning, the training data has the house prices. Now, the test data does not have the house prices, and the test data is actually a little bit of a misnomer because the test data set is what we're actually going to predict the house prices with, and we're going to submit our predictions to Kaggle, and they have the house prices, and they're going to give us a score. They're going to let us know how well we did on our prediction. So in reality, to us, the test data is not really test data, so I renamed it to the competition data. It's the data we're going to submit for the competition. Now, we will need test data, so what we're going to do is we're going to take that training data and we're going to split it into a train and test set to build our model with and to check the performance of our model. All right, without keeping you in too much suspense, let's look at the results. Now, keep in mind that this is from a fairly simple model. I've done some other models that had better Kaggle scores. However, this one was meant to be quick and dirty. Some things that I did not do was I did not scale the continuous data or introduce any interactions or polynomials. All right, but go ahead and look at the left table, 10 samples of predictions. Look at the first row, ID 530. It was off by 26%. This is not really good. However, look at ID 460. This one is almost spot on. That's amazing. Look at the right table, distribution of prediction variances. If you can see, looking at the bottom, the vast majority of the predictions are within 10%. So this simple model performs fairly well. All right, let's talk about how we got to those results. So let's dive into the training data. What we have here is a 5-row sample of the training data provided to us by Kaggle. We notice that there's 81 columns. Now, if we remove the first column, ID, and the last column, which is sales price, we're left with 79 features. So that's a lot of features to wrap our heads around. Right here is the MS subclass and the MS zoning features. One thing we want to do is try to determine if these are continuous or categorical values. MS zoning, we see RL, it's not a number, it is obviously a categorical value. Categorical values cannot directly be modeled in a regression, linear regression. So we'll have to change that. And then MS subclass is a number. It can be processed by our machine learning regression algorithm. However, a deeper dive determines that this is actually categorical as well. However, this got by me for this model, but I still got decent results. Lot frontage and lot area, okay, these are values that are clearly continuous. Over here, the pool, QC, fence, and miscellaneous features. They all have a bunch of NaNs. These stand for not a number. These we have to deal with. For this model, the approach I took is if it was a continuous feature, I filled it with zeros. If it was categorical, I filled it with missing. Before jumping into the code, I did want to just review linear regression very quickly on a high level. And basically, linear regression, the model itself uses calculus, but all you need to understand the model is basic algebra because it is based off of the formula of a line. I think I have a middle schooler that is studying this. Okay, it is y equals mx plus b. Okay, so y is the dependent variable because it depends on x, but in machine learning we call it y hat or the prediction. Okay, and x is the independent variable, and in machine learning we call this the features or inputs. Okay, m is the slope, but in machine learning we call it the gradient or weight. I prefer weight for this example. And b is the y-intercept, but in this regression example we find out that it is the mean. Okay, so y equals mx plus b is the formula for a line for one feature. But if we have multiple features, the formula ends up being y hat equals m times feature 1 plus m times feature 2 plus m times feature 3, and on for all of our 79 features plus the mean. Now let's switch it. Let's take this m out. That's something I learned in algebra, but now we are doing machine learning, and let's call it w because it makes more sense if we think of them as weights. So now we have y hat equals the weight times feature 1 plus the weight times feature 2, and on for 79 features plus the mean. Okay, so we see that basically our prediction is nothing more but the mean plus the weight of each feature. Okay, and that feature can be positive or negative, so it can increase or decrease the final value of the mean. All right, so the model, and just to let you know how this works, the model that we use comes up with the weights using a process called gradient descent, which involves calculus. But because this logic is already built in to the library of our model, we don't have to worry about it. All right. Now, not all features are useful for making predictions. In fact, they can add noise and cause something called overfitting. That's why I chose to do a Lasso linear model, because this reduces the weights downwards towards zero, and it actually makes some of the weights to be zero. So you do 0 times that feature and it makes it 0, effectively taking them out, which is a form of automatic feature selection. It's going to get rid of features that really don't have a strong relationship with the sales price. Okay, now we can, in our model, in our Python library, when we use the Lasso linear model, there is a parameter called alpha, which is the strength of that push downwards to 0. All right, let's dive into the code. So the first thing we do is import our libraries. All right, so let's look at a few of these. Import pandas as PD. Let's talk about pandas. So pandas is a library that has something called the DataFrame. The DataFrame is a container for data, a data object, and it has various useful methods for data, such as we can import data from file into the DataFrame. Okay, we can sort the data, we can slice and dice the data, we can add to the data, we can remove the data, we can do data transformations. We can think of it as a virtual Excel spreadsheet. I think that is a good paradigm for this data object. We can then take that data, we can save it, okay, as a file. We can save it to the clipboard. We can save it as a CSV file or a standard text file. It is very powerful. Let's skip down to the bottom from sklearn.model_selection import train underscore test underscore split. So if you recall, Kaggle gives us training data, okay? But what we're going to have to do is we want to split that training data into subsets, training subset and a test subset. Okay, so how this works is we actually do the train test split method, and we put into it a data frame. It's going to randomly select 75% of the rows, and it is going to return features for those 75%, and it's going to return the Y values for those 75%. It's also going to return features for the other 25% and the Y values for the other 25%. So we put in one data frame, it returns 4 separate objects. We are then going to train our model with the 75%, which we will call our new training data, okay? And then we can review the results, and then we can make tweaks until we feel comfortable. Then we can see how our model performs on the test set. Repeat the process, and when we feel good, then we know that we have a strong model. Now, from sklearn.linear_model, import Lasso. This is the machine learning algorithm for linear regression that uses a special L1 regularization which pushes down the weights close to 0 or 0, effectively making it an easy, quick, and dirty way to do something called feature selection. All right, so let's load our data, and let me show you how to read this. So I created a variable called training data, okay? And we're going to set that to the PD object, which is a pandas object, and we're going to use a method called read_CSV. We provide it with a path, which in this case is train.csv, which is the same data that I pulled down from the Kaggle website, okay? So it's going to take that, use that path, fetch the file, bring in the data into a data frame, and assign that data frame to the training data variable. Okay, so that training data from now on will be a data frame with the train.csv data, and we're doing the same with the competition data. Okay, that's going to be a data frame with the test.csv from Kaggle data. Okay, let's skip cell 3. Let's jump down to cell 4, where I will print the dimensions, or in data frame talk we call it the shape. So we list the data frame name, training data, and we say dot shape, and it gives us a shape. Competition data dot shape, it gives us a shape. So we look at the output, training data shape, rows, columns, 1,460 rows by 81 columns for the training data, and 1,459 rows by 80 columns for the competition data. This makes sense to us because we know that the training data has the sales price, where the competition data does not have the sales price, because that is something we have to predict. All right, so in order to get a sample, because we don't want to see all 1,460 rows of the training data, we can use a method called head. I also use a statement that works in a Jupyter notebook called display, which can display data frames in a very pretty way. Okay, so within that display statement, we say training data dot head, and the default is to return 5 rows. And if you look at it, it's very pretty. If you look between utilities and pool area, you will see these 3 dots, which means there are a lot of features in between those that it's not displaying. Okay, and that is because if we displayed all of those 79 features, it would just be way too much to take in. But if we really want to see all those features, okay, this is how you do it. pd.options.display.max_columns equals none. Now, when we display the training data and the competition data, the first 5 rows, it will show every column, every feature. All right, let's discuss cell 8. So if you remember earlier, we said that we would have to deal with these NaNs, these not a numbers. So this is the cell with the code that deals with that. So what we do, come to find out, if you say list parentheses this and then you insert a data frame, it is going to return a list, which is a built-in Python data object. Okay, it's just values and commas. Okay, it's going to return value and comma. Each value is going to be the name of the data frame column. So training data columns will turn into MS subclass, comma, MS zoning, comma, lot frontage, comma, on and on and on and on for, for this, the 80 features or the 80 items. Okay. So that's what training data columns is. So then we can loop through that with this 4C in training data columns, which basically is going to look at each item in the training data column list. Each item represents a column name, okay? Now, the other piece is if you say training data, which is a data frame, okay, and you have those brackets and you put in a column name, okay, then that means that from now on you are dealing with a column in that data frame. So then we use the .d type attribute, okay, of that column, and it's going to find out what kind of data type that column is set for. So what we're saying is if that column is an object, we're going to make the assumption that all objects are categorical values, okay? So what we're going to do is then we're going to use a method on that column, training data C, okay? We're going to use a method called fillNA or fillNA, all right? So whenever it finds what all NaN values in that column, it is going to replace it, okay? It's going to replace it with the value that I give it. The value I am assigning is missing, okay? And then the in place means that we're going to change that training data object value, okay? We're going to just change it. It will now be missing. We're just not going to do this and assign it to a new variable. No, we're going to actually change the training data object, okay? So if it is not an object, all right, if it's not categorical, then we're going to, for that column, all NaNs, we're going to replace it with a 0. And yes, we want to do it to that training data object, okay? So we are going to do the exact same thing for the competition data set. And that's how we're going to handle our NaN values. Now at the bottom you see we display both just to see what it looks like. All right, so here, this is where we're going to reassign the training data object, the training data frame. We're going to reassign it. So we're going to reassign it to the pandas.get_dummies method. We're going to pass in the training data frame, okay, with the training data. And what the get dummies does is it is going to transform all of the features that are categorical. It's going to take those unique values and create new features. And the values of those new features are going to be 1 or 0. And this will allow us to perform our machine learning linear regression with that categorical value now because they are continuous values. We do this both for the training data and the competition data, and then we display it to see what it looks like. Okay, and here is the same slide as previous, but I scrolled over so you can kind of see what the new features look like. You can see the new features uh, has a naming format, which is the old feature name with the underscore with the categorical value that it has. So MS zoning underscore C all, MS zoning underscore FV. That FV used to be a value under the MS zoning feature before we made this transformation. All right, and then so let's print the shape once again to see the results of our transformation. And wow, now we've jumped up to 305 features for the training data. And looking at the competition data, we have 292 features. Whoops. What's happened here? Ideally, not ideally, but we have to have these features match, okay? So they're not matching, and this kind of makes sense because the training data and the competition data may have the training data may have uh, uh, values for features that are not present in the competition data and vice versa. So we have to handle this. I guess there's various ways to do this, but what I chose to do was to just drop the features that are not present in both data sets. And the code, I will not go into too much detail. You can review that, but we did some set math, determined which values were not present in both, and dropped the features from both data frames in order to make them exactly the same. And the result is now when we do our shape, we have 285 features in both data frames, the training data and the competition data. Okay, and here is where we use the train test split. We put into it our training data frame, we put into it our sales prices, okay, and we give it a random state. Mine I just set at 0, and what will happen is that random 25-75% split um, will be the same random split every time for random state equals 0. Okay, if we want something different, then we have to choose a different random state. And since it returns 4 different objects, we have to provide it with 4 different variables to hold those objects. So they are called x underscore train, x underscore test, y underscore train, y underscore test. Okay. Uh, Next line of code, then what we do is kind of instantiate an instance of the lasso object, and we're going to call it my model. So the variable my model is now an instance of the lasso model. Okay, I put in it a parameter of 298.4. Now I actually am not showing you something. How I arrived at this is I did a loop, and what I did was I looped through all the different alphas until I got to the optimum alpha that gave me the best test score, okay? And that ended up being 298.4 for that parameter. It took a long time to run. That is why I did not show that loop here. Okay, so one thing is, if you notice, in order to build my model, we have to use the .fit method, which is going to be what actually determines those weights, or they call them in this model coefficients, x underscore train and y underscore train, which are the prices. You have to put those in separately. So x train, your features, then comma, and then your prices, your which you're going to want to predict. And so it sets the it uses that gradient descent and finds out the weights, and then it uses that L1 regularization to push those weights close to or to 0. Okay, and then once we do that, we can find out how well it does. So then we do the my model dot score, and we show X train and Y train. Okay, so now this score is going to show us how well our predicted price is fitting the training data, and it should be high. Okay, and then we're going to show the my model dot score, the X, put in X test, X underscore test, comma Y underscore test. So that's our test data, that 25%. Okay, and we're going to find out how well the test set scored. Okay, so if you look, we printed those out. You know, we scored a 90 in our training and a 74 in the test set. Okay, so one thing to note is that we also looked at the coefficients. So what I did was a count of all of the coefficients that were not 0. Okay, that's what that NP, that's the NumPy. We didn't talk about that much, but we're summing the model dot coefficients. This returns all of the coefficients, or all of the weights, and we're saying all of the weights that are not 0, how many of them were there? And it ended up being 68, meaning that in the end this model considered 68 features. We gave it almost 300 or over 300, and it's considering 68 of those. 68 are important to sales price. So we felt comfortable with the score. So finally, what we're going to do is create a new data frame called submission, because this is something that's required for Kaggle. We have to give them back our predictions. Okay, and we're going to say PD, okay, that's our pandas library, dot data frame. Okay, we're going to create a data frame. We're going to create it out of what? Out of my model dot predict method, which is going to now, we're just going to give it, we can't give it X and Y's, right? We're just going to give it the X's, which is the features of the, which is the data frame for the competition data. Okay, and then we will give those features a column name in the data frame, and we're going to call it, not those features, but I'm sorry, the predictions. We're going to give the predictions a name, and that's going to be called sell price. Okay, and then we're also going to throw in the indexes. The indexes were those IDs that were necessary for referencing. So we're going to give it the same indexes as the competition data. So we preserve those indexes in this data frame. And when I display the submission data frame, okay, the first top rows, we see that the format is perfect. It's 2 columns, just like Kaggle wants. It's the ID and it's the prediction called sales price. And then, as I said before, the data frame has a method to save the data frame as a file. And this file type that Kaggle wanted was CSV, so we're going to say submission.to_CSV and give it a file name, and it's going to save it into that same directory that this code is running in. Okay, so that is how we submit our predictions to Kaggle. Okay, wrapping this up, let's think about something I touched upon earlier in this, and that is the fact that, you know, we had, or at least I have very little domain knowledge in real estate, okay? And that's okay, because I want to use machine learning to look at the different features and understand the relationship with those features to the sales price, all right? So now that we have a model that's performing pretty well, we can kind of look at that. So, you know, once again, the weights in the Scikit Learn Lasso model is called the coefficients. So we can pull those out. We can look at the absolute values of those because we don't care if it's a positive or a negative. We just want to see the magnitude, okay? And if we sort all of our data and pull out the, the top 10 by magnitude, then we get this list that we see here, and it's very interesting. So if we look at that first item, remember, anything with the underscore was something that we engineered with that get dummies. So condition 2 underscore pos in, well, for that item ID 101, that used to be a feature called condition 2, and the value of that feature was pos in. But now we've engineered this feature condition 2 underscore pos in, and the value is 1. And if it has, so now any item that runs through our model that has condition 2 underscore pos in value of 1, we are taking that 1 times negative $61,000, okay? And that's eventually going to get added, or actually to the mean, which in this case, since it's negative, it's going to reduce the mean value of all the house prices in our set by $61,000 just because that categorical value was present. And the same as for neighborhood underscore no ridge, okay? So being in that no ridge neighborhood, we are going to add $23,000 onto the mean price of the house, okay? So this was very interesting. And so I hope that you found it interesting. I hope that you found this helpful, and I actually hope that you're able to use information in this video to create your own model, to create a better model. And I hope that you share those with me. Hit like, give me some feedback, some comments. But thank you so much for watching this video.